In the last problem we got two blocks of masses 2 kilos and 3 kilos, which are connected by a light string that passes over a frictionless pulley of moment of inertia 0.00400 kilograms per meter square and a radius of 5 centimeters. Then the coefficient of friction for the tabletop is going to be 0.300. The blocks are released from rest. Now, using energy methods, we will try to find the speed of the upper block just as it has moved 0.6 meters. So first release the values: mass 1, 3 kilos, mass 2, 2 kilos. Moment of inertia can be rewritten as 4 times 10 to the negative 3 kilograms per meter squared. And radius, it could be 5 times 10 to the negative 2 meters. One thing we should also notice is that in the mass of 2 kilograms, we have one tension that is going upwards to the cylinder, and we have the weight going down, but there is no friction. On mass 3 kilograms, we do have a friction, and they're giving us the value 0.3. And also, we have the weight going down. Now the equation that we're going to use is the net work equal to the change in kinetic energy. Now for the mass 3 kilograms, we're not going to use the weight as it produces a work of a positive work per se. For the 2 kilograms, as the tension is going up, the work is going to be negative. In the formula that we're going to use, the net force is going to refer to the external force. So as we know, the net force is going to be the work of the weight plus the work of the friction. But in this case, we're going to do the following. We're going to find the net work of the external force, and we're going to set it up equal to negative delta U, representing the work in the weight, and the work of non-conservative forces representing the friction, the work of the friction. Now, as we solve for the work of non-conservative forces, we can say that the change in the kinetic energies plus the change in the potential energy is going to give us the work. So the work of the non-conservative energy is going to give us negative friction times the displacement delta S. That's going to be equal to the final mechanical energy minus the initial mechanical energy. Now the friction is represented as the coefficient times the weight. And we just drop down the delta S. In this case, in the final final mechanical energy, we have 1/2 m1 v1 squared plus 1/2 m2 v squared, representing the kinetic energy. Then we're going to add up 1/2 moment of inertia times the angular acceleration squared. That's going to represent the rotational kinetic energy of the cylinder. Then we're going to add up m2 times g times h. That's going to represent the potential energy of the mass 2. So if we choose the reference at the floor, we end up with a height of negative value. Now, in terms of the initial mechanical energy, we have 1/2 n1 v squared plus 1/2 m2 v2 squared. But in this case, nor m2 or m1 is moving, and the kinetic energy of the cylinder has no value. Ever since we started on rest, we can say that everything that's supposed to go for the mechanical energy is going to be 0. The last thing we're going to do is plug in all these values that we found reading that question into our final equation that we have. In this step that I just did, I just factor out the final velocity, which is what we're trying to find. Then I did some algebra, and I have on the left side 6.6, and on the right side I managed to get a 4.1 times the final velocity squared. Now we just have to square root 6.6 divided by 4.1, and that should give us 1.27 meters per second as a final velocity. So we chose letter A because it's the closest to 1.27 meters per second. So 1.22 is the speed of the upper block just as it has moved 0.600 meters.